Okay, for step 3, this is a little bit of a complicated one. Remember that one of the criteria that she was specifying for bighorn sheep is that it should be far away from roads, it should be owned by the Forest Service, it should be forested, and the other major criteria is that it should be generally steep topography, that they like steep topography, not flat lands. And so this number 3 on here is going to account for how steep the topography is. Now, she's wanting us to use 2 tools in here. Well, really, it's 1 tool, but when you work your way through the tutorial, you would have created, or you will create this Sunday when you work on those tutorial problems, a slope GIS layer. Now, she's essentially is assuming that by the time you got to the exercise problems that you'd completed that step in the tutorial. And so, if you don't see a slope layer, it just means you hadn't got to that step yet, and it means you just have to run it. And so I'll have to do that for this demo because I don't have that layer made. The slope layer, this is a pretty clever thing about GIS, is that any raster GIS layer, one of the tools that you can use is called a neighborhood function. And that is that in the raster realm of all the values being defined, if you have a GIS layer that shows the elevation, where the topography is low and high, what the slope does is it takes any given raster cell and compares it to its 8 neighbors around it. And it basically says, of all the different directions, which of the 8 neighbors has the greatest elevation difference from that center cell. So it's doing a comparison between the center cell, all of its neighbors, and it tallies up and it says, which one has the biggest difference in elevation? And then it basically says, well, what's that difference? That's the rise. Takes the horizontal distance, that's the run, and it computes a slope from that. So the input is an elevation raster, the output is a slope raster. And in order to do it, it's doing a huge amount of mathematics in the background. For every single cell, it's going cell by cell, looking at the 8 neighbors, and then running the statistics, and then in the output, writing the slope to that cell. Then it goes to the next cell, writes the slope, next one, next. And so we can appreciate not having to do all that by hand as I hit go on this tool. Okay, so what we need to have for this third one, I'm just going to turn off my step 2. We're going to start step 3. If we don't see a slope layer already made in here, it means that we need to make it. We need to make it based on the topography GIS layer, this 30-meter topography layer. And one thing you'll notice, remember when we talk about rasters, this was a chapter 6 thing, when you bring in your first raster, it'll have a cell size, it'll have an extent, a north, south, east, and west border. But one thing what you might notice is that with this particular raster, there's no attribute table, it's grayed out. And if you remember from chapter 6, any continuous raster is going to be absent of an attribute table. There's no reason for an attribute table. It doesn't have any natural clusterings. Whereas a discrete raster, one that shows land use or roads or something that is discrete, then it will have an attribute table. So it all depends. But this is a continuous one. Every single raster cell in here is just its elevation above sea level. And if we zoom in quite close, it's kind of a neat pattern that emerges, kind of this dendritic pattern you can see. But if you zoom in close on this, you can actually see the individual pixels. And if you took out a measuring tool and measured across one of these pixels, it should come out to be about 30 meters. Just a quick measurement on there shows that that's 27.5, pretty close to the 30. Okay, but as I zoom back out, so what it's going to do is any given cell, if I was to click on that cell, this cell right here, for example, is 1,470, I'm guessing, meters above sea level. It would compare that number to its 8 neighbors and then compute the slope based on that information. All right, so that slope tool is found in the geoprocessing. Oops. And the input to the slope tool is a raster, so we want our 30-meter topo raster. It's going to make a slope. She suggests calling that output layer slope 30 meters. So I'll go ahead and use the name she was looking for. We want this to be in units of degrees. That is, degree slope. Remember, 0 degrees would be absolutely flat. 45 degrees would be at a 45-degree angle, an internal angle. 90 degrees would be a straight cliff at a 90-degree interior angle. So that's what we're going to be understanding the output units to be. All right, I'll go ahead and hit run on this tool. And so what we should expect to see when this finishes is a map that shows areas of steep topography shown here in these dark brown colors, some places here that are very, very steep. Any place in these bright light colored areas, those are less than 5 degrees of slope, so very, very shallow slope. These are going to be fairly flat areas shown in floodplains and on hilltops and so forth. All right, but this isn't the end of the story. This is in her description. This is the start of this one, is to have a slope layer. And what she wants to do is to calculate the average slope over 10 by 10 cells, and then create a Boolean raster showing where the average slopes are greater than 15 degrees. And so if we think about this, what she's asking us for here is generally, like, what's the overall slope? What's the average slope? Not on every raster 30 by 30 cells, but on bigger blocks that are 300 meters by 300 meters. What's the average underneath that? And so this we have to run something called block statistics. It's one of the tools you get exposure to in chapter 11. And it's a way to sort of downsample your data. You have high resolution data, in this case 30 meters. The output from this is essentially going to be like 300 meter blocks at a time. And so there's all kinds of applications of this. In this case, she just wants to see generally what's the average topography, not specifically at every cell, but in general regions. So we're going to use that block statistics tool back here. And that's going to be a geoprocessing thing. So we'll go back. Block statistics. The input raster for this is going to be that slope layer. It's going to make a GIS layer called block statistics. I'm just going to call this slope. And then I'm going to put 300 or 300M behind it for 300 meters. When you run these block statistics, the default is a rectangular box, but you can also do a wedge, a circle, irregular, or weighted. She wants this to be how many cells by how many cells. This isn't, you don't want 300 by 300 here, you want 10 cells by 10 cells, because each cell is the 30 meters. So 10 of those makes 300. But notice, right down here, unit types is cells. You might be able to put that to the map units, and then you could put it to 300. So if I'm keeping it with cells, I'll keep it with 10 by 10. And then she wants, I think in her example, she said the average, which same thing as the mean. Am I right about that? When people remember the problem? Did she say average? Okay. So what we can expect this to look like then is just a very, very blocky version of this same map when it comes out, when I hit the run button. So what it's doing is it's almost like it's putting a 300 by 300 over the top of those raster cells. And do you see how then it's downsampling the data? Generally areas that are very steep are coming out with these darker areas on here. Generally areas that are they're lighter colored. The areas that are relatively flat are coming out with the lower values on here. Like this whole region up here is generally flatter. So let's see if she wants anything else from that problem. If she wants that turned into a Boolean. Then create a Boolean showing where the average slopes are greater than 15 degrees. So remember that the problem wants only those areas that are steep slopes. So over 15 is what she's looking for there. So how would we create a Boolean out of this? Remember the last tool almost always in this, each of these steps has been the reclass tool. That's the way you turn it from a GIS layer that has numeric values into one, like continuous numerics, into a break where you convert into zeros and ones. My suggestion on all of these is change it here first. So go to the symbology on this layer. I'm going to turn that layer back on. Change it from stretched to classify into 2 categories instead of the 5. The reason I suggest this is because if you do this now, when you bring it into the raster calculator, it'll bring this in by default. And you can also get a preview of what you think it should look like. So here we're going to put in a threshold of 15, and so anything that's over 15 is shown here in red. Anything on average that's under 15 is shown here in yellow. And this is what Boolean's going to look like in the end, but we still have to do that reclassify step in order to get it to zeros and ones rather than these ranges. All right, so reclassify will be the tool we're going to use for this.
The input raster for this will be the block statistics, or block groups value is what we want here. There's our thresholds. The basically almost 0 to 15. Remember, that's not the areas that we want for bighorn sheep. That's too flat for them, so we're going to call that part 0. Anything that is over 15, she wants that as a 1. Not making this mistake I made last time, I'm going to hit the return on this to lock in that 1. And then we're going to call this output the results for step 3 results. I'm going to go ahead and hit run on this. If this works, we should have a map that looks just like this one. The colors might shift, and then also that we look at the legend, we see 0s and 1s. Those steep areas are areas that are 1s. The low slope areas are 0s. And just to clean up a little bit, I'm going to remove some of these layers that I made just to get to that last one. Move the slope. Then I'll go ahead and remove the topography. We can always add these back in later if we needed them. I'm going to go ahead and remove the roads and the vegetation. Okay, so what we have now is a Boolean for step 3, a Boolean for step 2, and a Boolean for step 1. We'll go back to the instructions to see what she wants next. Okay, so use the rasters produced in steps 1 to 3 to create a Boolean raster showing the potential reintroduction areas. Basically, this is just a simple matter of then taking all 3 of these layers together into one operation. Any place where a 1 was found in all 3 of those layers, the output from that's going to be a 1. If it encounters a 0 at any of those 3 layers, the output's going to be a 0. The way to get that is to do a multiplication. You just multiply those 3 layers together. So 1 times a 1 times a 1 results in a 1. Any place encountering a 0, the results in a 0. You could also do an addition. You could add them all up, and then you'd get ranges from some places that are always 0s, some 1s, some 2s, and some 3s, and then you have to do a reclassify that says anything that was a 3, call it a 1. Anything else, call it 0s. Either is going to result in the same. The first way I described it does it in 1 step. The second way you have to do 2 steps, so I like the more efficient route. We'll just multiply them. So this gets us to step number 4. I'm not going to stop the recording. I'm just going to go ahead and do this one because this is the fast part. There is a tool you will learn in the chapter called the raster calculator tool. It allows you to do, it's like in mathematics, you've heard of matrix algebra, where you're solving equations across matrix of numbers. Think of those matrices as just being rasters, and so you can do mathematics across multiple rasters. In this case, simply multiplying them all together is what you're going to do. But it's called the raster calculator. And you just build an equation in this box right here based on these maps. So we want the results from step 1. Just double click to bring it down. Times. Double click on the asterisk here for times. Double click on step 2. Times. Double click on step 3. And then this will be the answer for 4. So I'll call this one step 4 results. Okay, so we have an equation, step 1, step 2 times step 3. And if this works, we should get a raster out of this that's a Boolean itself. It should only have values of 0s and 1s, and they're places that met all of those criteria. Let's look at our legend. In fact, we see that that's right. We have a sea of 0s, and then these little islands here and there of 1s. These are areas that are owned by the Forest Service, that are forested, and that are relatively steep, and that are also away 300 meters from roads, meeting all those criteria. Now the last step, step 5, what she wants is anything that's under, I forget, we have to look at the number, but under like 3 square kilometers. Those aren't suitable places to release, even though it met all those criteria. It's not a big enough contiguous area, and so she wants us to then find those areas that are the bigger ones and only export those. But let's look real quick at what she wants. I think she might just want a screen capture of this from step 4. What's the total area of these potential sites? We have to answer that one. And then she wants us to capture the map. So we need to figure out a way to get the total area of these potential sites. A real simple way to get that total area is that in the attribute table, because this is a discrete raster and not a continuous one, this will have an attribute table. And if I open up that attribute table for the output from step 4, let me just zoom in on this. We end up with a count down here. And so the value, the majority of our area, total number of raster cells that do not meet one of those 3 criteria is this almost 400,000 cells. And then there's, of the ones total, all the purple cells added together is 65,000 cells. And so what she's asking you for, though, is an area, a total area of this. And so we have to take that 65,800 and whatever, and then multiply it by the area of each cell. Well, each cell is 30 meters on the side, so it's 30 by 30 meters. And so we just have to get out our calculator for this to do the math on that. And I'll try to see, where did my calculator go? I'm going to have to back out here. So we want this value. I think I can paste that in. And then we need to multiply that times 30. And then multiply that again times 30, because that's on 2 sides. And so we end up with 59,237,100 square meters of total area. She didn't specify the units, so this would be a suitable answer for the total amount of area that's shaded in pink on that map, areas that meet that criteria. Okay. And then moving on to step 5 then. So you'd end up, for the answer for that one, you'd capture this map, showing, make sure you capture the legend on here, so you show your zeros and ones, and then give that total numeric value. All right, last step then, when we go back to her book then, is the site must be at least 3 square kilometers in area to be considered for the reintroduction site. How many potential sites have a minimum of this area? And then create a helpful map of these sites that meet these criteria. She suggests converting the sites to polygons, looking at the map, what other factors might be used to select a final site. So basically, she's saying there's going to be too many sites. How do you narrow it down to which one to use? And so that's our task for number 5. The idea behind this then is she's giving you a hint that one way you can do this is convert to polygons. That's going to take each contiguous region, any areas that hold up as one little island of areas that work, it's going to make a polygon out of that. And then each of those discrete polygons, then you can just sort them according to how big they are, and then only select those that are over 3 kilometers would be the way that we can make this work. Okay, so I'll go back here. There are conversion tools in the geoprocessing. We want to do a tool called raster to polygon. That's this top choice here. The input raster will be the step 4 results. Now, if you want to exclude all those areas that are not that are the zeros in here, you just don't want to bring those along because those aren't going to be suitable areas, we can do a little trick, and that is select only the ones that meet the criteria. Now those have all become selected. Only those polygons will come along when I run this tool. So I'm going to say the result 4 step, it's going to be the value is the field that we want to use for this, and this is going to be an intermediate step that's trying to get us to, so this is going to be suitable areas and then polygons. And this essentially is step 5. Okay, there's a check mark here next to something called simplify polygons. We can leave that in. Basically, this is to say, instead of aliasing all along each one of those 30-meter cells, it'll just kind of round everything off. Just looks a little nicer. If there's some reason you don't want that and you want it all pixelated, you can uncheck that, but you can see why that's the default on. And then we actually do want to make this, no, we don't want multi-part features. We want to have it where every polygon is its own. I just want to explain what that one is. It is possible in GIS where you can have multiple polygons all act as one unit. That is to say, like, if you had a GIS layer of states,
you can imagine you don't want where every individual polygon is a different row in the attribute table. For example, the Hawaiian Islands, you'd like that to hold together, even though it's multiple polygons. You want all those islands to say that's all Hawaii. It turns out there's a lot of states that have little isolated pieces of them. Even Illinois has a few little pieces where the Mississippi River has shifted, and they're little isolated pieces. They're still part of Illinois, and you don't want each of those to become their own polygon. Each one get their own row in the attribute table. That's what multi-polygons are. In this case, we don't want that. We want every polygon to stand alone as its own, so that way we can sort out which ones are over 3 square kilometers, and which ones are under. So I'm going to leave that intentionally turned off, and I'll go ahead and hit run on this. It should make a GIS layer of just those polygons. If I turn off the raster now we see only those areas that are meeting all those criteria. Now it's a vector, not a raster. And in this attribute table, we should see that there's a column in here for each of those polygons. What's the area? The only problem we have at this moment is the units on this are in square meters still, and we want this to be in square kilometers. So we just need to look up a quick conversion. This should be a simple conversion. I don't know what I did there. I would think that this would just come up right away. Wait. Oh, wait. We're on square meters, rather. Okay, my bad. All right, it's just to and then -6. So, so for example, we will put in here, what we have to do is that two-step process, guys, where the first step is to add a field. And we want this to be in, this is going to be area underscore, and then it's square kilometers. And we want this to be, instead of long, we want this to be a float. This is going to add a new column onto our attribute table. We have to hit the save button up here to get that to lock in. And then we can close the fields view, and now we have this new column that's blank at the moment, but we'll be using the shape area. So we need to do calculate field. And for this, we'll take the shape area and then divide by, let's see, what does it turn out to be? So it's 1,000 by 1,000. So what does it come out to be, 1,000,000? Do I have that right, guys? Check my math. Does that sound right? I wonder if I have one too many. Let's see. Is it 100,000? No, it should be 1,000,000. Why am I struggling with this? Well, because she wants anything over 3 square kilometers, so that does make sense. So we have some. Like, it's only going to be what those largest of the polygons. We end up with those few selections that are over the 3 square kilometers. Okay. So of those however many are selected there, then the last part of the question is, so she wants that count as one of the parts of the answer. By the way, it's 6. And then she wants to know, basically based on whatever logic, there's not going to be a right or wrong answer on this one, what other criteria could you use to decide on which of those 6 to actually do for the reintroduction? You just have to look at the map to decide which, a logic for what other factors could you use to decide on which one of those to pick. So go ahead and just, be creative about how you might
choose one of those over another. I mean, for me in my mind, if there's clusters of those areas that meet the criteria, maybe that's better. They would actually have more area that they could roam into if that actually gives them more territory. On the other hand, if you were trying to study them and you wanted them more contained, maybe you would use the logic of having one of these more isolated ones as the one that's kind of an island of what works in an area that doesn't work around it, something like that. So again, no right or wrong answer on that. Just use the logic that you'd want to use for that last part. But at least that one, to get the total number, that's the way you go through it. Convert from raster to vector, and then once they're in polygons, then add the new column, get the units right, and then sort for which ones are over 3 kilometers. All right. With that, let's just I'm going to pause the recording here. We'll save that out as one